Welcome to the deep dive. Today we're tackling a really fascinating question. How close are we to a truly accessible world for individuals with visual impairments?
And what are the most promising technologies? The ones that can actually help us get there.
Exactly. We've gathered a whole stack of research, academic papers, reviews, looking at, well, everything from smart city planning.
All the way down to wearable tech and AI learning tools.
Right. The goal here is to pull out the most important insights, sort of get a handle on the current landscape of assistive technologies in this area.
It's pretty remarkable, actually, how many different angles researchers are coming at this from. It's not just one single solution.
No, it's a whole range, isn't it? Each trying to solve different pieces of, well, a very complex puzzle.
It really underscores the challenges people face navigating the world without sight.
Okay, so let's start big picture. This idea of inclusive smart cities, or ISCs. It turns out cities are being looked at based on, well, how much they're thinking about and actually doing when it comes to including everyone, especially those with disabilities.
Right. The research we looked at sort of breaks them down. 3 levels.
Level 0.
That's basically a city not even considering inclusive design in its smart city plans. 0 awareness.
And level 1.
That's where there's awareness. They understand it's important, but there aren't really any actual strategies or actions yet.
Like Charlotte, North Carolina, back in 2016. They had a vision, but no concrete steps.
Exactly. A vision for inclusive neighborhoods, but no real plan to make it happen at that point.
And then you get level 2.
Level 2 is awareness and action. Tampa, Florida, again in 2016, was an example. They had, I think, 8 proposed strategies for an inclusive smart city.
That's quite specific. And what's interesting is that apparently over half of the early smart city proposals actually included actionable strategies.
Yeah, so it wasn't just talk, which is encouraging.
This way of categorizing cities seems really helpful for tracking progress, right? And seeing where we need to push.
Definitely. It highlights that making cities truly smart means being deliberately inclusive. It takes real action, not just, good intentions.
So thinking about those 2016 examples, it's been nearly a decade. Are we seeing a big shift towards level 2? Or are lots of places still kind of stuck at level 1?
That's a really good question. What are the hurdles stopping that progression? Something to keep an eye on.
For sure. Okay, moving from the citywide view down to more specific tech. Let's talk about localization, finding out where you are.
Yeah, there's some really clever stuff happening here. One approach combines cameras, IMUs, that's inertial measurement units,
Right, motion sensors.
and ultra-wideband UWB sensors.
And the clever part is how they combine them.
Exactly. It's a range-focused approach. Instead of just trying to pinpoint an exact location, they really focus on the distance data from the UWB. They then blend that distance info with the visual data from the camera and the motion data from the IMU, using a kind of mathematical cost function.
And that works better.
The research suggests it does, yeah. More accurate over time, less likely to drift, compared to methods that just focus on getting that initial precise position fix.
So it's more about tracking how far you are from things rather than always knowing your exact spot on a map.
Kind of, yeah. Think about it.
Yeah.
If you know your distance to a few fixed points, and you know how you're moving relative to them, which the camera and IMU help with, you can track your movement really well, even without a perfect starting coordinate.
Right. Cleverly mixing the data gives a clearer picture.
Especially over longer paths. And what's also exciting is the potential for using this with, say, multiple robots working together.
How so?
Well, if robots can sense their distances to each other using UWB, it could help them map an area much more effectively. Maybe build a combined map, even if they don't all see the exact same things.
Wow, okay. That sounds like it could be a game changer. Not just for robots, but maybe for personal navigation aids too.
Absolutely. The potential is definitely there.
Now, another big area is the Internet of Things, IoT, and how it intersects with healthcare accessibility.
Yes, IoT is making waves in healthcare. The research highlights some key plus points.
Like convenience.
Convenience, definitely. And automation for repetitive tasks, which can free up people's time and energy. Plus, many IoT devices are designed to be wearable or modular.
Adaptable to individual needs, which is crucial in healthcare.
Exactly. And another really important factor mentioned is scalability.
Meaning they need to be able to grow beyond just one user.
Right. For these IoT solutions to have a wide impact, they need to be scalable to meet community needs. An app that only works for a few people won't change the bigger picture much.
Makes sense. Okay, let's switch gears slightly. How do people actually interact with all this technology, this idea of multimodal human-machine interaction, HMI?
This is fascinating. It's about using multiple ways, multiple modes, to communicate with machines.
Like talking and gesturing.
Yes, at the same time. Combining different inputs means the system gets a richer understanding of what the user intends. It can even fill in the gaps if one input is, say, a bit unclear.
Like pointing and saying, "What's that?"
Exactly. And we already see bits of this in everyday tech, right? Things like leap motion or Captive Glove for gesture tracking.
And voice assistants like Siri or Alexa, which sometimes use voice and touch.
Precisely. And the research shows that combining modes like this can actually lead to fewer errors.
And faster task completion, too.
Yes, compared to just using one mode alone. There was an experiment, Rob, I think. People controlled a robot using both speech and gestures via Microsoft Kinect.
And it showed a clear benefit.
Quite clearly, yeah. Significant improvements.
But speech recognition itself still has challenges, doesn't it? The research mentioned that.
It did. And that's a really crucial point for inclusivity. Accuracy can vary a lot based on accents, or even if someone's voice is a bit shaky.
So how are researchers tackling that?
Well, one interesting angle is using socially inspired rewards, kind of like how humans use conversational cues. Applying that idea in reinforcement learning to help robots better understand voice commands. Systems like TownInfo and Marty are exploring this, trying to make the interaction more robust.
And it's not just voice and gesture. Touch is in the mix, too.
Definitely. Like the IRM robot controlled by speech and just a single touch point.
Okay.
And there's work on using speech and gesture for navigating virtual 3D environments, VGIS they call it, Virtual Geographic Information Systems.
Could make those virtual worlds more accessible.
That's the idea. Reduce errors, open it up to more users. Even for controlling media centers, TVs, music, they're exploring interfaces using touch, maybe even haptic feedback.
That sense of touch.
Yeah, alongside voice commands. Could be great for users with visual impairments, maybe even replace remotes eventually.
So the core idea is flexibility, giving people options, adapting to their needs.
Pretty much. And they're even thinking about robots as actual travel assistants for blind travelers.
Using multiple inputs there, too.
Physical interaction, verbal commands, digital info, the works. The big advantage of these multimodal systems is definitely efficiency.
But there's a catch.
Well, for critical applications like in healthcare, these systems absolutely have to be robust, foolproof really, able to handle all sorts of varied inputs reliably.
That makes sense. Okay, let's zoom in on something ubiquitous. Mobile apps. Making them accessible for blind users is obviously vital.
Hugely important. The research mentions the standard accessibility tools, gesture control, text-to-speech screen readers. We know about those.
But there's a new framework proposed, a distributed user interface.
Yes, this is interesting. The idea is to let parts of an app's interface UI elements be customized and even spread across different devices.
Like your phone and your smartwatch.
Exactly. And potentially even allow input from a caregiver. The goal is to simplify the interface, keep things consistent, and make it context-aware.
So tailoring the controls and info to the device and the situation.
Precisely. Making the user experience much smoother. And the results they found were pretty striking.
How straight?
Task completion time improved by about 28%. That was over 9 minutes faster on average, using these simplified interfaces compared to standard ones with accessibility services.
Wow, 28%. That's a massive improvement.
It really is. Although the research did note that some tasks, like editing text or deleting things, were still tricky, even with the simplified approach.
So great progress, but still some hurdles to overcome for a truly seamless experience.
Always nuances to consider, yeah.
Okay, shifting focus again, but sticking with smartphones. Let's look at the bigger picture of how they can function as assistive solutions.
Right, tackling everyday challenges, reading labels, identifying money, navigation. Smartphones offer real potential for independence.
The research highlighted some specific examples.
Yeah, some clever ones.
Yeah.
Like NavTap, a text entry system, uses a keypad where vowels act as anchors to help you find the other letters without looking. And multimodal eye-free interaction using 3D radial menus. You navigate with gestures and sound cues tell you what you've selected.
Gestures worked better than just sound.
Apparently so, yes.
Yeah.
More effective. Then there's MoBraille, connecting Android phones to Braille displays over Wi-Fi.
Expanding app accessibility.
And BrailleBack, an Android service that works with TalkBack for better Braille and speech interaction, and even Just Speak using voice commands to control on-screen elements.
It really shows how these devices we all carry can become powerful assistive tools.
Absolutely. And beyond that, there's research using the phone's camera for obstacle detection.
Giving warnings.
Yeah, through verbal cues or even haptic feedback, like a gentle push sensation guiding the user. And even intelligent glasses converting visual data into tactile feedback.
Amazing potential in the devices we already have, but what about the physical world itself? Our sources looked at inaccessible public spaces,
This is such a critical piece. We can have great tech, but if the environment itself is a barrier,
especially for users of mobility assistive devices, MOBADs. Their numbers are increasing, right?
yes, but urban environments often haven't kept pace. A systematic review found substantial inaccessible elements are common.
Like what specifically?
Pathway characteristics, uneven surfaces, lack of curb cuts, boarding ramps, entrance features like heavy doors or steps, confined spaces like restrooms, service surfaces being too high,
And the impact is significant.
hugely negative effects on quality of life, physical health, mobility, ability to use public transport. It all suffers.
So the built environment itself is a key factor in disablement.
Absolutely. The research concluded that very clearly. Technology is only part of the solution. Physical accessibility is fundamental.
Okay, related to navigating the environment, there's SLAM technology, simultaneous localization and mapping, used a lot in autonomous vehicles.
Right, and there's potential crossover for assistive tech here.
Like LOAM, LIDAR odometry and mapping.
Yeah, Lomium is one real-time SLAM solution. Uses 3D LiDAR and IMUs for accurate mapping and localization. It performs pretty well, especially with IMU assistance.
Though G-mapping was better in some specific cases.
In small-scale, low-speed environments, yes. But the point is, robust SLAM techniques like these could be incredibly valuable in assistive navigation devices.
Imagine a smart cane or wearable that builds a detailed 3D map as you move.
Exactly. That could be revolutionary for navigating unfamiliar spaces.
Speaking of which, our sources specifically address the challenges visually impaired individuals face in unfamiliar places.
It's a key point. The white cane is essential, but often not enough in a totally new environment.
People rely more on cited guides or landmarks.
Yes, cited guides or environmental information they can perceive. It's different from familiar spaces where they build confidence using a mix of senses, feeling, counting steps, timing.
A mental map, almost.
Right, and complex indoor places like university buildings where things get moved around. Those are particularly tough.
Really highlights the need for tech that provides that extra layer of spatial awareness. It makes me think, maybe coordinating multiple devices or sources of information could help, like that research on multi-UAV path planning.
That's an interesting parallel. Even though it was about drones collecting data from IoT sensors in cities.
The year-band 50 scenario.
Yeah, planning paths in a complex map, avoiding buildings, no-fly zones, limited flight time. The core challenge is efficient navigation and coordination in a complex space.
So the principles might apply.
Potentially. Maybe coordinating a handheld device with fixed environmental sensors or getting dynamic updates for navigation. It's about managing information flow in tricky environments.
A team of assistive devices, maybe? Okay, focusing back on individual navigation, specifically indoor route planning for visually impaired users.
There's been a lot of work here. The most common factor route planners optimize for is distance, usually combined with obstacle avoidance.
But other factors matter too, right?
Oh, definitely. Safety of the path, number and angle of turns, landmarks, environmental cues like floor textures, floor transit features like stairs or elevators, even crowds.
And route complexity, cognitive load.
Exactly. How hard is it to remember? How much mental effort does it take? Even environmental details like lighting can be considered.
The idea of routes following walls came up too, helpful for cane users.
It often is, yeah. Some algorithms prioritize wall trailing, obstacle avoidance, and landmarks. But the research also cautions against assuming everyone wants to follow a wall all the time.
Universal preferences are rare.
Pretty much. So we need more research on how to weigh these different factors, how to integrate diverse user needs. Collaboration with end users and orientation and mobility experts is key.
That user-centered design point again, it keeps coming up.
As it should.
And related to that, smartphone cameras being used as electronic travel aids, ETAs.
Right. A systematic review looked at the state-of-the-art computer vision software running on phones for this purpose.
And they included user surveys.
Yes, which is crucial. Defining the evaluation criteria based on actual user needs and expectations. Making sure the tech aligns with what people actually want and find useful.
Now, moving into something pretty futuristic, generating 3D indoor scenes from depth images.
Yeah, this is cutting-edge stuff. Using a generative model AI trained on semantic segmented depth images.
Meaning images labeled with object types and distances.
Exactly. The system learns from these and can then automatically generate plausible 3D objects within a specified room size. Uses a type of AI called a volumetric GNN.
What's the potential application here for accessibility?
A big one could be creating realistic virtual environments for navigation training. Imagine practicing navigating a specific building virtually before you go there physically.
That would be incredible. Okay, a different kind of challenge, making visual data like charts and graphs accessible.
This is a huge barrier. So much important information is presented visually, often without a text equivalent.
So researchers are looking at alternatives: sound, touch.
Yes, things like tactile graphs, text descriptions, audio graphs where sounds represent data points. Synthesized speech and braille are common too.
But they have limitations: cost, special devices, maybe not capturing the nuance.
Right. Traditional methods like braille or tactile graphics can be expensive or difficult to produce accurately.
One method mentioned involved using OCR on chart images to generate XML.
Yes, optical character recognition reads the text and structure. It then creates an XML file containing the chart's title, the labels, like product names, and the actual data values, pixel counts, percentages,
And having that structured data makes it easier.
to generate accessible alternatives. Structured audio descriptions, potentially input for tactile displays. Yeah, it's a smart way to extract the core information.
Very clever. Okay, another really advanced area: neuromorphic wearable devices. For healthcare.
Neuromorphic computing is inspired by the brain. The big advantage is power efficiency, making it great for edge computing on wearable devices.
So doing complex processing locally on the device itself?
Exactly. Combining advanced sensors, biologically plausible learning algorithms that learn like the brain.
Like STDP, spike timing dependent plasticity.
Yes, STDP is one example, a learning rule where connections strengthen or weaken based on the timing of signals or spikes.
Yeah.
It's well suited for these event-based neuromorphic chips.
And these chips are showing promise.
Definitely. Processors like DynapSE have been used to classify EMG and ECG signals, recognize hand gestures, with good accuracy and much lower power consumption than traditional systems.
And the ability to keep learning is important for wearables, right?
Crucial. They need to adapt to the user and the environment over time. Brain-inspired algorithms offer potential for this continual learning.
Still challenges, though.
Oh yes, making algorithms robust to hardware variations, efficiently encoding sensor data into spikes. But the potential for ultra-low power adaptive wearables is huge. New memory tech might help too.
Fascinating stuff. Now back to localization beacon networks. How are they used for blind navigation?
Beacon networks, Bluetooth, UWB, involve placing small transmitters around an area. A device listens for these signals to figure out its location.
How accurate is it?
Bluetooth beacons achieved around 1.65 meters average accuracy in one study. An airport trial using beacons successfully guarded users, but they found challenges at door entrances due to those meter-scale errors. Precision really matters in tight spots.
So good, but maybe not always precise enough.
Potentially, yeah. Which is why non-visual feedback is also explored.
Like vibrations instead of audio, especially in noisy places.
Exactly. Vibrating belts, even vibrating handles on mobility aids. Users seem to prefer handle-based vibrations in some studies. Systems use haptics or braille displays to convey obstacle locations too.
Okay, and AI is also getting involved in guidance directly with deep reinforcement learning, DRL.
Right. Framing robot navigation as a sequential decision-making problem. A POMDP, partially observable Markov decision process, solvable with DRL.
So the robot learns to guide through trial and error.
Essentially, yes. Using LiDAR data and goal info as input and robot velocity as output. User studies showed people had confidence in these DRL-based robots, especially with UWB sound beacons adding context.
They found them useful.
Yes, particularly in unfamiliar places, though they suggested improvements like gentler audio cues and making the robot multifunctional.
And dynamic obstacles were still a challenge for some systems.
More so for SLAM-based localization compared to UWB positioning, apparently. Moving things mess up the map.
Makes sense. Finally, let's touch on gait analysis, predicting thigh angle.
Yeah, using harmonic models. Based on data from just a single stride, they can predict the thigh angle waveform pretty accurately.
High correlation, low error.
Yes. Analyzing individual strides like this offers potential for detailed gait assessment.
How could that help in assistive tech?
Maybe for personalized device tuning or for fall detection systems. Understanding gait patterns in detail could be really valuable.
Wow, we've covered a huge amount of ground today, from city planning right down to analyzing individual steps.
It really shows how multidisciplinary this field is. So many different areas of expertise coming together.
And we didn't even fully delve into AI for neurodevelopmental disorders, though it came up.
Right, personalized tools for conditions like ASD, ADHD, dyslexia. Using AI for emotion recognition, focus improvement, social skills. Personalization is absolutely key there.
Cloud systems helping deliver those tools too, while raising data privacy questions.
Always ethical considerations with AI, especially involving young people. Privacy, data security, informed consent, crucial things to address. But the cloud offers benefits like cost effectiveness and real-time feedback.
And underlying so much of this is that user-centered design principle again, eliciting requirements directly from users.
Absolutely critical. Getting feedback from visually impaired individuals and maybe even non-VI users for remote support aspects is essential.
Like the Inarasi SAS concept mentioned.
Yes, user feedback on prototypes showed satisfaction with usability and accuracy for obstacle avoidance, but also highlighted needs like accurate navigation info considering obstacles and clear feedback on interactions.
So, wrapping up, what are the core components, the essentials for these assistive devices?
The research really boils it down to three things: the navigation module for wayfinding, environmental perception using sensors and processing, and the user interface for feedback.
And they need to be safe, reliable, real-time.
Accurate, resilient, work in diverse conditions. It's a tall order, but that's the goal.
So we've taken a deep dive into, well, a really inspiring range of technologies, all aimed at making the world more accessible for people with visual impairments.
From that big picture of inclusive smart cities right down to the nitty-gritty of neuromorphic chips and gait analysis.
The common thread seems to be empowering independence, enhancing quality of life through smart, inclusive design and tech innovation.
And it's striking how interconnected it all is, isn't it?
Yeah.
Progress in self-driving car mapping like SLAM.
Could directly benefit personal navigation aids.
And what we learn about human-computer interaction, speech, gesture, haptics, feeds back into designing better assistive devices.
Okay, here's an intriguing detail for you, our listener, to ponder. Imagine combining that precise UWB localization
with AI-powered object recognition, knowing what's around you.
all in a single wearable device. A system that doesn't just guide you accurately, but actually describes your surroundings in detail, anticipates your needs, helps you understand unfamiliar places in real time.
That really leads to the final, maybe provocative thought. As these technologies race ahead, how do we ensure the focus stays locked on genuine user needs, on ethics?
How do we create solutions that aren't just technically brilliant, but truly empowering and inclusive for everyone?
And perhaps, what role can you, our listener, play in shaping that future of accessible technology?